Good day. This is Bruce Fridman from Arizona State University. I'm the PI on a recently completed CERDIP limited scope project number ER2721. The title of our project is Synergistic Reductive Dechlorination of 1,1,1-trichloroethane and trichloroethene and Aerobic Biodegradation of 1,4-Dioxane. This was a joint project between our team at Arizona State University and a team at Florida State University. Besides me at Arizona State University, we had Dr. Rosa Krochmalnik-Brown, Dr. Chen Zhou, and Mr. Yihao Luo. And at Florida State, we had Dr. Yunong Tang and his student Boyo Wang. So the challenge we have here is dealing with the combined contamination of 1,4-dioxane plus 1,1,1-trichloroethane, we'll call that TCA, and trichloroethene, we'll call that TCE. This is a very common problem because the solvents TCA and TCE often were contaminated with 1,4-dioxane as a stabilizer. Therefore, groundwaters contaminated with either or both of the chlorinated solvents also contain 1,4-dioxane. What we want to do here is to develop a platform to be able to remove all of these compounds, completely detoxify the groundwater so that it can be reused and not a hazard to people or the environment. So our approach is to create a synergistic platform. That platform features an anaerobic reduction of TCE and TCA to ethane, followed then by an aerobic biodegradation of 1,4-dioxane in an oxygen-based reactor. In the first stage, the hydrogen-based stage, we tested two different systems. One is a strictly biological system. That's the hydrogen-based membrane biofilm reactor, or MBFR. And then we also tested a very novel approach, the hydrogen-based membrane palladium film reactor, or the MPFR, where palladium is an abiotic catalyst for reducing the TCE and the TCA. In the aerobic stage, we used an oxygen-based membrane biofilm reactor to completely aerobically degrade and mineralize the dioxane plus any residuals that came from the first hydrogen-based stage. In our research, we conducted parallel modeling studies, that's mathematical modeling studies, and experimental programs to test both stages and then the combined synergistic platform. So in the studies, first, for the hydrogen-based reductive stage, we tested the membrane biofilm reactor and the membrane palladium film reactor. Both of them worked. However, the MPFR, the membrane palladium film reactor, was much more efficient in terms of kinetics and in terms of the complete conversion of TCE and TCA to ethane. So based on that technical performance as well as techno-economic analysis we did, we chose the novel MPFR as the first stage for the reduction of TCE and TCA to ethane. We also tested the aerobic stage in the oxygen-based MBFR, and we found that it was very effective at oxidizing 1,4-dioxane, as well as any of the residual materials that would be carried over from the first stage. Finally, we put the systems together. We delivered water contaminated with TCE, TCA, and dioxane first into the hydrogen-based MPFR. There we had very good results. We got about 96% removal of the TCA and the TCE, and we had very strong selectivity towards producing ethane as the final product. That was about 93% was converted all the way to ethane. we had very small residual concentrations of intermediates, dichloroethene and monochloroethene. Then that effluent, which also still contained the 1,4-dioxane, was fed into the oxygen-based BFR, where we completely oxidized and mineralized the dioxane below the detection limit of our analytical methods, and we also removed all the small residuals of the coming from the hydrogen-based system here. The fact that the MPFR produced ethane was very important and valuable because ethane is an important co-substrate for the oxidation of the 1,4-dioxane here. So we showed here that our synergistic platform works. We could first do reductive dechlorination to ethane of the chlorinated solvents, and then we could do oxidative mineralization of 1,4-dioxane plus any residual products in the oxygen-based MPFR. So this system can be used for pump and treat of groundwater. In principle, it could also be adapted for in situ bioremediation using the same principles on this. And we also, besides showing the synergistic platform for the removal of the chlorinated solvents and dioxane, we also presented a novel new system, the membrane palladium film reactor, which no one has tried before, and it's a very promising means for doing any kind of palladium-based reductive dechlorination. Thank you for listening, and we hope that you've enjoyed this brief audio summary of our project.